Hey class, Adam Ward here. I want to talk with you today about fluid mechanics, and in particular we're going to talk about dimensional analysis. This is the first in a series of videos that I'm going to put together on this topic. This one is to give you background and motivation. So why are we doing this? What are we talking about? Subsequent videos will show you how to generate your own dimensional analysis and how to use those for scale modeling, for example. So in preparation for this lecture, I'd like you to learn a little something about the Marmot Dam removal. Wherever you're viewing this lecture, you should also have received, if you're in my class, you should have received a heads up from me to watch at least one of these videos, but I want to post them here so that you all could pause the video. If you don't have a lot of time or effort to put into this, that National Geographic summary is only a minute and a half long, but it gives a nice overview. And similarly, there are some other resources on the web. There's a project site from the U.S. Geological Survey, a site from the Sandy River Watershed Council, who did a lot of the advocacy work and funding for this. And at the bottom, you can see that there's a report from National Center for Earth Surface Dynamics, or NCED, who built the physical model. And that report's really nice because it actually shows you how a model gets used in practice. So the idea of modeling and similitude, and those are concepts that we'll talk about in our next lecture. So in short, the Marmot Dam, you can see up here on the top right of your screen, this is what the Marmot Dam looked like. Big concrete structure, a large river backed up behind it, the Sandy River. And what was done here was first to build a cofferdam behind it, or a temporary dam behind it. Second, remove the dam itself, so go in and take out all of that concrete and as much of the man-made structure as you possibly could. So you can see a view of that cofferdam now down on the bottom. And then the water would flow from behind the dam around through this bypass channel. And the idea here was you wait until a big storm hits. So in this Pacific Northwest, that's in the fall when a large rain events start to come back in. It's a Mediterranean climate. And so you would make a small breach on this earthen dam, so let it start to overtop. And after that, you let nature do the work. So erosion and a pulse of both water and sediment will then travel downstream through the channel. Just to show you what actually happened, so this was in mid-October 2007. These are time-lapse photos of the day that they breached the dam. So you waited until the right storm event occurred. You can see there's the cofferdam intact in the top left. You can see water actually seeping through the temporary dam, so it's filled up behind there and water's starting to come through. Out on the dam, you drive a small excavator and with a brave operator who actually makes a breach or makes a cut in the top of the dam, and then nature starts to wash this downstream. So the motivation here, the reason we're taking a look at this, is how do you plan something like this? This is not a simple system. It's not an idealized pipe with an idealized fluid flowing through it. In fact, what you've got here is a really complex problem. And you get one shot at doing this dam removal and you want it to go right. You may see my helper Charlie in the background here. So you want to model this. And there's really two ways that we do modeling. One is with computer models. So we try to describe the physics of the problem as best we can and solve a system of equations. But what also happens in complicated problems is we build scale models. So scale models are, maybe think like you've built a model car or a model airplane. So a scale model is used to replicate what will happen in the system and study it at a scale that's economically feasible to build and to test, so that you can make predictions about what will happen in the real world. And so that report from NCED and the video of the scale model being built was part of the planning process here for the Marmot Dam. So this becomes helpful the idea of scale models and what you need to get right when we think about a complicated system. So if you had one independent variable and one dependent variable, you could conduct a series of experiments and get a cloud of data that might look like I've shown here in red. And you might say, well, okay, I can see that relationship. You'd fit some line through it and say, good. If I change the independent variable, this is how the dependent variable would respond. For example, in the Marmot Dam removal, this could be the peak discharge on the x-axis and the time until failure of the dam on the y-axis. Right? And so with one independent variable, this is a pretty easy system. But that's not how our complex dam removal project behaves. Right? We might have to think about the grain sizes in the riverbed sediment itself, about cohesion. So how easy is it to stick those grains onto or slip them past one another? What time of year is it going to take place? How wet will the dam be? So there's a whole host of concerns that you might have when you're trying to design something like this. And as soon as you go from one variable to more, your life gets pretty difficult. So here's our same plot. Independent variable number 1 on the x-axis and a dependent variable. But now if we consider there's some other variable. So in red here I've labeled these as independent variable number 2 at its first value. So maybe this is cohesion of the sediment. Well, then you'd want to systematically vary that too. So you might vary it at 2 or 3 or several values for the second independent variable. And what happens is you get exponential growth of how many experiments you would need. So for one independent variable, let's say that you feel comfortable with 10 experiments per variable. If you have one independent variable, you would need 10 experiments. If you have two, you would need 10 to the second power or 100 experiments to cover that parameter space, because you'd want to test independent variable 1 across its entire range. And for each of those values, you'd want to test variable 2. So this one you could think like you're going from making one row on a checkerboard to an entire checkerboard. And as that number grows to 3 or 4, the number of experiments you need to conduct grows exponentially, right? We go from 100 to 1,000 to 4 independent variables would be 10,000, and it gets out of hand. So the idea of these dimensionless variables is that they help us reduce this parameter space. Rather than taking all these variables individually, we put them together in groupings so that we can manage the number of experiments that we would need to do. Now, things that we'll have to consider, we'll have to consider geometric scaling, so getting the sizes correct. So we want a scale model that looks proportionally like the full scale or the real dam. We want to get the dynamic scaling correctly, so the forces are all proportional to one another. We don't want the relative importance of gravity to shear stress to change between two things that we're considering. And we need to get kinematic scaling right, so all of the time scales, things like velocities, accelerations, for example. So before we get into sort of design of models and using models to make predictions, which will be our next topic, I want to talk a little more about dimensionless numbers with you guys. So we want to get all three of these correct, and these will play into how we make dimensionless numbers. Yeah. So grouping variables to simplify the parameter space. So one example of this that I'd like to show you, a really common one, is called the Reynolds number. And so what we are going to do here is we're going to watch this video clip, and what you have happening here is you have flow moving from left to right on the screen, and we've got a small streak of green dye being released. So as I play the video, what's going to happen is the flow rate through this pipe is going to be slowly increased. So here it's flowing very slow. You can maybe just make out some waves moving through there. And as the flow increases, so discharge through this tube is going up and up and up, you can see that that flow gets more and more turbulent We continue to accelerate the flow, and we continue to get more random turbulent motion and mixing. And you can see that based on the dye. Okay. So what describes this problem? If we were trying to sort of take this set of observations, where from relatively slow to relatively fast flow, you went from this orderly, nice, sort of consistent streak of dye to the really turbulent flow, what might matter here? It's not hard to imagine some of the key elements might be what is the fluid. So what I showed you was a video of water, but if we change that to oil or corn syrup or air, you might expect different results. The velocity seemed important. We know that was changing through the video clip. And the geometry of the problem. So that was one size tube. Would that happen the same way if the tube was larger or if the tube was smaller? And so the way that we combine these things all together is into a dimensionless group called Reynolds number. And so Reynolds number I've written for you here is density multiplied by velocity of the fluid multiplied by the pipe diameter d, all divided by the viscosity of the fluid. So fluid properties circled in orange, fluid velocity, I've got the green arrow pointing to, and pipe diameter blue. And what this does is it says, look, if you want to know something about the system, you don't need to study the fluid and the velocity and the pipe diameter. Just tell me what the Reynolds number is. That's a good indicator for me. I don't really care about the specific fluid or the specific pipe. What I care about is this ratio that is Reynolds number. And later in this class, we'll look at Reynolds number as we predict things like energy losses associated with turbulent flow. So this is an example of the sort of dimensionless grouping that might shake out as being really important. In building a scale model of the Marmot Dam, we might have checked to make sure the Reynolds number in our scale model was the same as the Reynolds number that we saw out in the field, in the full-scale dam. And to prove to ourselves that this is dimensionless, what I'm doing here is taking the density of that fluid in the first term, so mass per unit volume or mass per length cubed. Velocity is length per time. Pipe diameter is a length. And a viscosity has units of length multiplied by time per mass. And just to see that, I'm proving it to you in orange here. If you look in the front of the textbook that my course is using, it's described as a force time per length squared. And because I'm working with masses, I'm just swapping out force for mass multiplied by length over time squared. And I remember that because force equals mass times acceleration. So that's how I think about switching my F's to M's or my M's to F's in a problem. So we can go through here and we can cancel out those 3 L's on the top with 3 L's on the bottom, T's and M's, and prove to ourselves it is indeed unitless. Okay, so at this point I'm hoping that you agree with me these dimensionless numbers might be handy. They can help us simplify relationships. They can help us make sure that our model systems are representative of the important characteristics of the real systems that we're trying to explain. And the way that we get around to this is a process that's called Buckingham's pi theorem. And so this is named after Edgar Buckingham. Buckingham was a bit of a Renaissance man as far as scientists go. So he had expertise in a host of different areas. After doing his PhD work at, I believe it was Leibniz in Germany, he worked for the USDA's Bureau of Soils, and then he spent a majority of his career at the U.S. National Bureau of Standards, which is now an organization called NIST. And this is a place that basically ensures that we understand how to make consistent measurements. So this is Buckingham. It is his pi theorem that we use. So what is this Buckingham's pi theorem? Well, there were a few scientists who were thinking about these dimensionless numbers or ratios in specific fields. It was Buckingham who generalized this approach and said, hey, you can use this for a lot of things. This is not just electrostatics. It's not just for fluids. It's a more generalizable, transferable scheme. So his work is to help us understand how can we generate dimensionless numbers. And this is pretty cool because these dimensionless numbers can be helpful to us even if we don't understand the relationship. So, in other words, at this point in the semester, you don't know much about turbulence, but I've already told you that this Reynolds number is a key description, right? So these are like summary statistics. You don't have to understand everything about a relationship to still take advantage of the fact that one does exist. And personally, I find this really cool because it starts to unlock the potential for scale models and empirical data. And of course, this was all done well before there was any microprocessor. So scale models were really, really important. This was how you might design a bridge or design a building or design a large piece of infrastructure. You would model it at scale in the lab and hope that that was representative of what happened in the field. And Buckingham's pi theorem gives us a way to formalize that process of knowing that something was representative. Okay, so Buckingham's pi theorem in 8 steps. I am not going to go through all of these steps in this video. So there is a series of examples that I will share following up on this. In the very first example problem, I will talk through each of these steps in a very explicit way so you can see each step, exactly what's happening, and you can use that as a model for future problems. In subsequent examples, I'll be a little less explicit about telling you I'm on step 5 or I'm on step 3, and hopefully you'll be able to pick out how these steps are actually happening. So that's what I've got for you here. Thanks for listening along and watching along, and at this point you should be prepared to look at example problem number 1 along with me. I'll see you there in a few minutes. Thanks all.